What's going on, everybody? This is your pal Dr. Withrow here with the first of what will most likely be many lectures in statistics here in our statistics class for the spring 2020 semester here at ECA. I hope you all are well. Let's begin. We are going to be starting a new chapter here now on something called the normal distribution. And we've been talking about this at least peripherally throughout the course of the semester here, but now really for the first time we're going to discuss it in depth, and we'll describe exactly what that's all about here. There's a video that I posted for you to watch prior to this. Hopefully you had a chance to watch that. I know that we showed it earlier in the semester as well. Hopefully it's a somewhat familiar video to you by now, and it was well worth your time. Let me start off here by giving you an example. What I'm showing you here is a picture of my middle stepson Bradley here. Looks like he's playing skip-bo with us right now and enjoying himself, most likely because he's beating the pants off of each one of us here. Bradley is my middle stepson, and at 6 foot 8 inches tall, he is the tallest person in our immediate family. So the question that I have going into this lecture here, how unusually tall is this? We can say that somebody is tall, we can say somebody's large, short, thin, fat, whatever, but the art of statistics allows for us to attach some numbers to that. What do we really mean when we say that Bradley in this case is very, very tall? How tall is he in comparison to other Americans, other people around the world? That's one of the things that we can get from statistics here. So that's what we're going to be discussing here with the normal distribution. It's going to give us some tools to be able to describe exactly how tall he is compared to other Americans. That's going to be coming at the end of the lecture here. But for now, let's spend some time taking care of ourselves here. Let's focus on clearing our minds, focusing on our breathing, and making it so that we are completely alert and ready for this upcoming discussion. Welcome back. Let's discuss this in detail here now. In previous discussions with the we've been talking about discrete data when it comes to probability here. If you recall, we've been dealing with all these probability distributions that we put together here, which described rolling dice, flipping coins, pulling cards out of a deck, asking the number of heads that you're going to get, the number of tails you're going to get, the number of clubs you're going to get, the number of sixes you're going to get, the number of times you roll 2 dice and you get 12 or 7 or things like that. These are all discrete forms of data, and we've been working with that really up until now. And it's allowed for us to describe these probability distributions, as you recall, in the forms of tables where we have discrete probabilities for each one of these categories. What is the probability of rolling 2 dice and getting a 7? What's the probability of getting a 5, and so on and so forth? These are discrete probabilities that we've been working with here. And so you can see that up until now we've been working with discrete data. And I'm showing some examples here that I mentioned before, number of hearts or clubs drawn from a deck. And doing this allows for us to describe these things in terms of a binomial distribution. That was that distribution that we were talking about near the end, where the mean is equal to n times p and the variance is equal to n times p times q. We talked about that near the end. That's the binomial distribution. When we're dealing with continuous data sets, now we're going to be working not with the binomial distribution, but with, you guessed it, the normal distribution. That's the most common distribution that we use for describing this kind of data. And it looks like my computer's locking up right now. This will be interesting right here live while I'm recording. This is lovely. So let's see here. Not seeing a whole lot of crazy stuff going on. I think iTunes is going crazy on me right now. I think that's what it is. But I can't advance my slides. Oh, there we go. Here are some examples of continuous data. We've been talking about this sort of thing throughout the course of the semester here. Height and weight, test scores, temperature data. That tends to be, continuous data that we're working with here. Stock behavior, as well as totals of dice. Sometimes business performance, how it does in the stock market, how it does with sales, how it does with quality, those kinds of things. And lastly, some manufacturing accuracy. How often is that you manufacture a part that's supposed to be these specific specs? Well, we know that parts aren't always manufactured to exact specifications, and there's always some percentage that have to be discarded or sent back for further testing at the very, very least. So that's a common issue there, and that's something we can describe using a normal distribution. And I'm still having problems here with some things. A common probability distribution, like I said, is the normal distribution. Again, this is called the Gaussian distribution. We'll keep working with this as best we can here. Again, this was the video that I had you take a look at earlier on here. I'm not going to have us watch it again here, but it described really the origin of the normal distribution, really what it is more than anything. If you can imagine taking an infinite number of dice, and you've got a great big set of these, and you roll all the dice at once, and you count up all the numbers that you see that you rolled for each one of those dice, and you add them up, and you record that score on a sheet of paper. You grab up all those dice again, and you have them all in your hand, and you throw them down to the ground again, and you calculate the sum of all of those dice once again, and you write that down, you grab them up again, and you throw them down again, and you do this, 1,000 times or so. You're going to get, if you were to plot the distribution of all those values of the sum of all those data, of all those dice rolls there, it's going to take the shape of a normal distribution. That's essentially what this is. So the sum of all those dice rolls will tend to follow a normal distribution. As you recall, when we were taking a look at just one die, then it's just an even distribution. It's flat like this. When it becomes two dice, then it becomes a pyramid shape like this, centered around the sum of 7 for 2 dice. And as you start to look at 3 dice and 4 dice and 5 dice, now it becomes a distribution that has more of a curvy bell curve shape like this. Let's see what's going on here. Okay, let's see here. So here's what it looks like. Like I said, it looks like a bell curve. And they have different sort of shapes and sizes to them. Actually, let me show you the screen here. Duh, should probably do that. Some are tall and skinny, and some are short and fat, but they have the essentially the same shape to them, if you can see that here. I'm actually showing you three different normal distributions. They're all centered around 0. They're all symmetric. Remember, we were talking about that's one of our terms here. It's not right skewed and it's not left skewed. It's centered right in the center there with a symmetric distribution, so it's kind of even on both sides. You could put a mirror here down the center and it would pretty much look the same either way. It's also unimodal in that there's not 2 modes or 3 modes or 7 modes. It doesn't go up and down, it just goes up once and then comes down. So that's another aspect of this as well. And you'll see that the only difference really between these 3 normal distributions is that the bottom one here, the third one that's yellow, is spread out. And that's because its value of standard deviation is larger than the others. So it pulls it apart just a little bit more than the other 2. So here we can see here, this distribution has a mean of 0, but a standard deviation of 1. This one here that's a little bit wider has a mean of 0, now a standard deviation of 2. And lastly, this third one has a mean of 0 and a standard deviation of 3. You can also have normal distributions that are the same size and shape, but also located at different places here. These 3 normal distributions have the same standard deviation, they just have different means, don't they? They're centered around different places on the x-axis here. This one has a standard deviation of 1, but it has a mean of 4, so it's centered around this mean here at x equal to 4. You probably can't read that, those numbers are so small there, but this is actually -4 on the x-axis here. This one in the middle that's red also has a standard deviation of 1 but a mean of 0, so it's centered right here in the middle. And then lastly, this one to the right has a standard deviation of 1 and a mean of 4. So once again, is each normal distribution unimodal, bimodal, or trimodal? And is it left skewed, right skewed, or symmetric? Hopefully you can see and see from our previous discussions here that the answer to the first question is unimodal, and the answer to the second question here is symmetric. Some other characteristics of normal distributions: these distributions are bell-shaped, as you already know. They have their means, medians, and modes are all at the same point here. Especially when you have a distribution that's skewed to the left or skewed to the right, then its mean and median and mode will all be in different places. They'll be spread apart from each other. But when you have a nice symmetric distribution like this, that mean, median, and modes they line up at the same point, which is right at the center. It's a continuous distribution, which means that there aren't any gaps in the distribution. Believe it or not, that actually is not true for all distributions, but for this one it is. It's continuous. There's a value at each location. It's infinitely wide. You've seen the bell curve here, and we've talked about its general shape. What I haven't perhaps talked about enough is the fact that it actually is infinitely wide. That distribution extends out to infinity in this direction and in this direction as well. So it spreads out very, very thinly out to positive infinity and to negative infinity. It's one of the interesting things about the normal distribution there. And even though it spreads out, it never goes negative. It gets closer and closer to 0, closer and closer to the x-axis like this, but it never touches the x-axis, never goes to 0. And lastly, if you take a look at the total area under the curve, the total area under the curve is actually just 1, or 100%. Now that might seem a little strange for me to talk about area under a curve. You've probably heard of areas of rectangles, that's being length times width, or areas of circles, that's pi r squared. some formulas along those lines, but you've probably never heard of somebody talk of the area under a curved shape. How in the world do you calculate that sort of thing? Turns out you don't learn how to calculate the area under a curve until calculus. There is a way in which you can do it, but as it turns out, if you took a normal distribution and you scooped it up, from one side to the other side, and you smushed it together into a square, that square would have a length of 1 on one side and a length of 1 on all the other sides as well. A length of a height of 1 and a width of 1, so an area of 1. Interestingly enough, it's just the way that a distribution works. And so that's very, very important when it comes to probability theory, because as you recall, when we have a probability distribution, all of the probabilities everywhere have to add up to what? They have to add up to 1, don't they? All probabilities of all possible events always have to add up to 1. And so it's important that all of those, all that area under that curve also adds up to 1. Okay, once again, it's always symmetric like you see over here. You can see that when you have something that's left skewed or right skewed like this, that causes the mean and the median and the mode to kind of separate from each other like this. And the mode is always the most popular value, so it's always going to be right at the tip of the peak, no matter where it is. So it's way out here in front. The mean is usually going to be somewhere, hanging back a little bit, and the median in this case will be somewhere in between the two. That kind of gets reversed when we're dealing with a distribution that's not left skewed, but right skewed. But when you have something that's nice and symmetric like this, that mean, median, and mode just lines up in the same location. And this talks about what we were describing before here. The normal distribution, you can see it's kind of centered around here or so, but the important thing I want you to see here is that, yes, this looks like it's hitting 0, but it's actually not. The values here of this distribution continue to be very, very small. They do not go to 0. They never cross the x-axis, and they go out to positive infinity in this direction. In the same way, it actually goes out to negative infinity in this direction, using smaller and smaller positive values, but never going to 0 and never touching the x-axis. So how do we calculate this distribution? Well, we've worked a little bit in things like Google Sheets and Excel earlier in this semester here. There's actually a mathematical equation on how you derive it. I will not expect you to remember this or learn this, but this involves the number e, which is kind of like pi in that it extends forever without any kind of a pattern here. You probably already know that pi is like that, 3.14159.265, blah, 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 blah. It goes on forever. So you can see pi showing up here in the equation. You can see e here showing up in the equation. It's the mean and the standard deviation are showing up here. They get squared before you take e to this power, and it gets divided by the standard deviation here, and as well as the square root of 2 pi. There's a lot of stuff going on there. You don't have to worry about that too much, but I just wanted you to see what that equation looks like. But here is how it's calculated. If you want to know what this value is right here of this normal distribution, the proper command for it in Google Sheets as well as Excel is this command, norm.dist, normal.distribution. And what are all these numbers here? Well, -2 is what the x value is, so that's where that is. And what are the other things you need to know in order to be able to calculate this curve? Oh yeah, you have to know what the mean is, and you have to know what the standard deviation is. That's what these things are. The mean and the standard deviation are the second and third parameters here. Probably just a good idea to remember here that for creating this graph here, you just want to leave this value false here. I'm not going to explain really why at this point here. So in fact, you can actually take a look at this Google Sheet that I created here. Sorry that it's just kind of a crazy link here. I'll put this link up in D2L so that you can take a look at it as well. But that's going to show you a set of normal distributions that you can change the mean and the standard deviation of. You kind of move them around the x-axis to see how they behave. Just create a copy of this and start playing with the means and the standard deviations of up to 3 different normal distributions on the same graph there. So you can see how these things really function. So even though some of them are tall and thin and some are short and fat, they're actually all essentially the same shape here. If I have these 3, for example, these 3 normal distributions here, they all have the same standard deviation. They're just located at different places on the x-axis here. Same thing with these 2. They're a little wider, but they're on different parts of the x-axis, so they have different means. Same thing with these down here. So if I subtract off the mean from each one of these data points, remember we did that a little bit when we were calculating variances earlier in the semester. We would subtract off that mean from each one of the data points so that we would have departures. And then we had to square them and add all that up and all that sort of stuff. But we, when we're subtracting off the mean here, then we're going to get a distribution that doesn't look like this or like this. It's always going to be centered around 0. Because these things are always now, we're describing departures around the mean. Is this thing bigger than the mean? Is this thing smaller than the mean? Well, if you're finding the departure from the mean, what's going to be the average value? It's just going to be 0, something that's right on the mean. So you can see that's going to be the case for each one of these here. And so if you were to, these distributions here now show departures from the mean. And if you take each one of them and you divide each one of those departures by the standard deviation, now all these distributions are going to look exactly the same here. This is called, now we're talking about deviations from the mean in terms of the number of standard deviations here. Let me get rid of myself here so you can fully see this here. So this distribution here now shows the deviations from the mean in terms of number of standard deviations. So if I've got a data point here that's sitting right here, I know that's a data point that was larger than the mean, and it was larger than the mean by about 1.5 standard deviations. So if you can do that with each one of your data points, you're always going to get something that looks like this. And this standard normal distribution is what we call a, well, interestingly enough, we just call it a standard normal distribution. It's a normal distribution with a mean centered around 0, and it has a standard deviation, nice and neat. It's a standard deviation of just 1. So each data point in this distribution now shows how many standard deviations the original data point was from the mean. All the stuff that's over here was bigger than the mean. All the stuff that's over here was less than the mean. Stuff that's over here was much less than the mean. Stuff that's over here was much more than the mean. More specifically, something that's right here was 2 standard deviations above the mean. Something that was right here, data that's right in here, was 1 standard deviation above the mean, and so on. So we can go through that process that I mentioned to you before that showed all of those distributions sort of collapsing into each other by taking each one of the data points here. Let me get rid of myself so you can see this formula here. Taking all of the data points that we have, x, you subtract off the mean, and once you have that deviation, take that deviation from the mean and then divide it by the standard deviation. You're going to get departures from the mean in terms of standard deviations, and you're going to get a distribution that looks like this. But that's all well and good, all right, but how do we calculate probabilities with this? Remember the problem that I had you take a look at with Bradley, who is 80 inches tall? How do we, he's obviously comparing his height to other heights here in the country, which are definitely distributed according to a nice normal distribution. But where is he in that normal distribution? Is he way off to the right? How much off to the right is he? So how do we use this normal distribution to calculate probabilities? Well, here's how we do this. Take a look at this problem here. I'm showing you just a simple wall clock, and this is a wall clock, let's say, that's powered by a battery. And eventually this battery is going to go dead, and when it does go dead, we want to ask the question, what is the probability that the minute hand here will land in a specific location. More specifically, what's the probability here that the minute hand is going to land and stop somewhere between the numbers 2 and 5? Interesting problem here. If we take a look at that here, this is noon, this is 1, 2, 3, 4, 5, all the way up to midnight, or from midnight to noon, depending on how you look at it. There's a 1/12 probability chance of the minute hand stopping somewhere between 1 and 2. And again, a 1/12 chance that it's going to stop somewhere between 2 and 3. And a 1/12 chance that it's going to stop somewhere between 3 and 4. And so on and so forth. So what is the probability that it's going to stop somewhere between 2 and 5? Well, that's this section right in here, isn't it? So it's a rectangle that has a certain area to it, 1/12 in this direction and 3 in this direction. So the probability of the minute hand stopping between 2 and 5 is equal to the area of the distribution between 2 and 5. 1/12 times 3 is 3/12 or 1/4. Now that makes sense, doesn't it? I mean, from 2 to 5, that's 1/4 of the entire circumference of the circle, isn't it? That's from here to here. And so it makes complete sense that there would be a 1/4 probability that this minute hand is going to stop somewhere between 2 and 5. So this just kind of makes the point here. There's an equal probability that the minute hand will stop anywhere on the dial. So this is going to be a flat distribution, just like when you were rolling that single die. 1, 2, 3, 4, 5, and 6, they're all the same probability, so this is a flat distribution. So, and the total area under the distribution here is 1, since it's got to land somewhere. So we know with 100% probability it's going to land somewhere. All of these possibilities have to sum to 1. So that means that this rectangle has a width of 12. That means it's also got to have a height of 1/12. So you can see that there's a connection there between calculating areas under these probability distributions and calculating a probability. So we find probabilities of specific things happening by finding the area under a specific part of the distribution. I know that sounds like a lot of technical jargon here. It's going to become easy as time goes on. Let's take a look at this standard normal distribution. And again, this is just a standard. This is a normal distribution here with mean at 0, and it has a standard deviation of just 1. So you can see here, what am I showing? I'm showing you here the percent of the data within each one of the sections here. 34% of the data is here between the mean and 1 standard deviation here below the mean. 13.59% of the data is somewhere between 1 standard deviation less than the mean and 2 standard deviations less than the mean, and so on and so forth. So we've taken a look at this to some extent already. We've calculated this area before here. This is right around the mean here, plus or minus 1 standard deviation. What's the area of this curve? What percentage of the data is sitting inside this part of the curve? And the answer is, we've been talking about this, it's about 68% or so. In the same way, and so 68.26% of the data will occur within 1 standard deviation of the mean. What does that mean for probabilities? It means that there's a 68.26% probability that any item of data will be within 1 standard deviation of the mean. So what's the probability of a new piece of data sitting somewhere inside of this 1 standard deviation of the mean? The answer is it's got a 68% probability of being somewhere in here. Let's take a look at 2 standard deviations from the mean. Here we have to add up 4 sections now, and that all adds up to 95.44%. So that means that 95.44% of the data is within here, or another way to say that, there's a 95.44% probability that any item of data will be within 2 standard deviations of this mean. Okay, you can probably guess what this next one is going to be all about. Now we're taking a look at 3 standard deviations from the mean here. Now we have to add up 6 different sections here, and we get 99.72%. notice that we're getting closer and closer to 100% as we're going out. We're never going to hit 100%, but we're going to get closer and closer to it. 99.72% of the data is within 3 standard deviations of this mean. So that means that the probability of any new piece of data occurring somewhere in here between -3 times the standard -3 standard deviations less than the mean and 3 standard deviations bigger than the mean, that's going to be a 99.7% probability that we're going to see that data in that region somewhere. Now you see these bell curves in different forms. If I make myself go away here so you can see this. This is just another one that's on the internet here. I know these numbers look different, but they're actually the same here. This is 0 right here at the mean. This is 1 standard deviation, and they're just making a half of a standard deviation jump here from here to here, different than this, which takes a 1 standard deviation jump from here to here. Just to bring this home a little bit more here, 19.1% and 15%, if we add those together, that's the same as our 34% that we've got in here. So they're just breaking it up just a little bit more here into more discrete pieces, smaller pieces like this. But they all add up the same way. The numbers are the same. So think about this. What is the probability that a new item of data will be in this shaded region here? How would we calculate that? Well, we are 2 standard deviations on one side of the mean and 1 standard deviation on this side of the mean. But really the procedure is the same, isn't it? We've got 3 things to add up, and the answer that we have here is 81.85%. Now I want you to get the connection here that this is the probability that any piece of data is going to be in this region here, and also that this is the area under this part of the curve here. The area under this part of the curve is 0.8185. That's that probability. It's going to be less than 1 because the whole thing adds up to 1. We have less than the whole thing, so our answer is going to be less than 1. More specifically, it's going to be all 3 of these things added together, which in terms of a decimal, not a percent, is going to be 0.8185. There's a relationship there between the area under the curve and the probability. How about this one here? Here's a chance for you to do this one on your own and to see how this works out here. What is the probability that an item of data will be in this shaded region right here? Whereas you can see this section right here, this is actually the probability associated with this section here between 2 standard deviations and 3. Take some time for that. Welcome back. This is a problem very, very much like the one that we were looking at previously. You can see here that we're looking at somewhat a lopsided portion of the normal distribution here, but that's okay. We know what these area distinctions are, and we know what the percentages associated with each one of these. So we're adding up the percent areas underneath the curve in each one of these 4 sections, and we're getting 83.99%. So yeah, just under 84% of the area of the curve is within that blue area. There is an 84% probability that any piece of data is going to be located somewhere between 1 standard deviation below the mean and 3 standard deviations above the mean. Remember, once again, this distribution extends out to positive infinity in this direction and to negative infinity in this direction. This distribution is infinitely wide, and so keep that in mind. So this thing is going to get smaller and smaller and smaller as it goes in this direction here. It's going to get closer and closer and closer, and there will be tiny, tiny little components here of area that'll get smaller and smaller and smaller. It's going to get like 99.99999999999% of the entire area under the curve as you get out to 12, 13, 14 standard deviations outside of this thing. But we're never going to actually get to 100%. So here's a little bit of a scale that we can use to describe this a little bit. Take a look at this here. What this is, this number here, is the total percent of the total area extending from negative infinity in this direction, all the stuff that's to the left of the screen here, all the way up here and ending here. This portion of the area under the curve is just 0.1% of the total area of this normal distribution. So if I use this here, for example here, and remember this goes out technically way out to infinity in this direction here, but it stops here, that's going to be 0.1% of the total area under this curve. All right, and so we say this by saying that the probability of any z value less than -3. In other words, any value for a piece of data that is less than, that is smaller than 3 standard deviations below the mean. That's what this z means here. So any piece of data that is smaller than something that's 3 standard deviations below the mean, well, the answer to that is just 0.1%. And that also means if we're taking a look, for example, at 1% here, if we're extending things, from the left and stopping here, now we have 1% of the data that we're looking at. Now, if we have 1% of the data in this direction, then what percent of the data is at this point but extends to the right in this direction? If this portion is just 1%, then what portion is this yellow section here? Well, the answer is that this is what we've talked about as being the complement of this. And so its probability is going to be 100% minus this 1%, or 99% of the probability. So simply put, if this section in here that ends here is just 1% of the total area, then that means that this yellow part here has to be 99% of the probability. This has to be the rest of it, the 99% probability for the area under the normal distribution. Let's go a little farther in this direction here. Here we're going to stop at this point. So how much of the area under this total normal distribution here, how much of the area under the curve starts here at negative infinity and ends at this point here? Well, the answer to that is 5%. 5% of the total area under the normal distribution ends here at just somewhere between -2 and -1 for a value of z here. -2 and -1. So it's somewhere between 2 standard deviations below the mean and 1 standard deviation below the mean. Kind of closer to 2, isn't it? But that's going to be 5% of the data here. And in the same way, if this portion that we just saw was 5%, what portion is this yellow section here? Well, it's going to be 95%, 100 minus 5. So 95%, the remaining 95% is going to be from this point to the right. How about here, where we stop actually at a z value of 0, where we are right on the mean, neither greater than nor less than the mean. We're right here on the mean. Well, what percent of the total area under this curve do we have to the left here? Well, this is a symmetric curve, so everything that's over here has to be over here. This has to be exactly the same as this, which means that half of the area under this curve has got to be on this side, with the other half being on this side. Notice down here, this is 50%, or half of the area under the curve. So in other words, the probability of something, some new piece of data being less than the mean is 50%. That's true for a symmetric distribution. When it's a normal distribution like this, that's true. So the probability that z is going to be less than 0, z is going to be something negative, in other words, something's going to be less than the mean, is going to be 0.5. Let's go a little farther here now. Now, is this area going to be less than 50%, or is it going to be more than 50%? Well, hopefully you can see that it's crested the peak here, and it's now on the right-hand side of the distribution, and so its cumulative area should now be above 50%. Its total probability should be now also above 50%. In fact, how much bigger? Well, it ends here at just shy of 1 standard deviation, so its z-value here looks like it's about, I don't know, maybe this is 0.5, that's 0.75, maybe it's 0.8 or 0.85, something like that. So, about that on this scale here. But if we come down to this scale here, that says 80% of the data is from here to the left. So we can see that here. How about this section here? Now we're really starting to get to, almost all of the, sizable portion here of this normal distribution. So we're ending here at this point, so our z-value looks like it's somewhere between 2 and 3. Here's 2.5. Maybe this is about 2.25 or so. So somewhere between 2 and 3 standard deviations above the mean. So how much data is somewhat less than that, ending at this point? Well, the answer here is 99%. And as we move to the right, you can keep going here. We're going to get closer and closer to 100%, aren't we? But are we ever going to get there? The answer is no. Now let's do some more complex ones here. How would we find the area in this part of the curve here? Just this part here. Not extending in this direction or in this direction, just this part in here. Well, here's something to keep in mind. This portion all the way to the left is 95% of the total area under the curve. And this area from here to the left is 70% of the total area under the curve. So how would we find this area? Well, hopefully you can see that it's this number 95 subtracting 70%. That's going to give us just this slice right in here, isn't it? So in this slice of the normal distribution, we are dealing with only 25% of the data. That kind of makes sense here, about 25% of the data within this slice right here. How about this part of the curve? Well, here we're going from about here. Once again, that's about 70% of the data is from this point all the way to the left, and about 10% of the data is somewhere from this point in the curve all the way to the left. So how about this section in between here? Well, hopefully again you can see that it's 70 minus 10, or 60% of the data sitting inside this portion of the normal distribution. Here's some more examples here. As it turns out, we can actually get more accurate information here than this sort of coarse scale can provide here. And these come from the normal distribution charts that I've given to you on D2L as well, where you can look up some z-value here. And again, I've highlighted these z-values here in yellow. 4 standard deviations below the mean has a z-value of -4. 3 standard deviations below the mean has a z-value of -3, and so on and so forth here. So you can use this chart here to find information more accurately than before here. So these values down here are our z-values from before. And let's see here. let's see if we can figure out the probability that some data is going to be somewhere in this region here, ending at 2 standard deviations below the mean. So we're asking here the probability that the z value here is going to be somewhere between, is going to be somewhat less than -2, I should say. Well, we can look at it on here, and it's going to say about 2.3%, isn't it? On this sort of coarse curve here. We can get a more accurate answer if we take a look at this z value and look up here at the table. -2.0. Notice what this is up here as well. If I look here, that's -2.01. This is -2.02. This is -2.03, and so on. So if we're going to find -2.00, that's this right in here, this value right in here, 0.0228. So we got kind of close here with this coarse scale here of 2.3%. A more accurate figure here is 0.0228. So let's try to find the area under the curve somewhere from z is equal to 2.5. You can see we're right in between -2 and -3. We're right in here, right in between 2 standard deviations below the mean and 3 standard deviations below the mean. And right in here, z is equal to -1.46, so a little bit less than half the distance from 1 standard deviation below the mean and 2 standard deviations below the mean. So somewhere in here. All right. Well, we know how this works here, where I would extend this line here, and it's going to be about, looks like about 7% of the data is from here to the left. And if I extend this down here, it's going to be somewhat less than 1% of the data is from here to the left. So in finding the area between these two things, it's going to be about 7% minus 1% or so. I'm being really sort of crude here at this point, but it's about 6%. We can find this a bit more accurately, again, by looking these things up on our data table here. -2.5, that's our first location right here. -2.50, that has a value of 0.0062. So it's actually substantially less than 1 here. So 1%, I should say. So that's where that is right here. And then if we take a look at this other one, it's -1.46, -1.46, so that's 0.0721. So yeah, it's about 7%, a little bit more than that. But this is the number, and this is the number. These are the two numbers I'm going to be subtracting in order to get my real answer here. So the probability that something is going to be between -2.5 and -1.4, right in here, is going to be this probability of it being -1.4, that's this right in here, subtracting off the probability, this smaller probability that's going to be -2.5, that's 0.0721 minus 0.0062, that's 0.0659 or 6.59%. So try this one here. You're trying to find the area under the curve here between these two locations. Z is equal to -3.15 and Z is equal to -1.1. Take some time for that. back. This is another good problem here in calculating those areas in between two locations on the standard normal distribution curve here. You can see right on here that we had two boundaries that we were looking at, and we simply just had to subtract the cumulative areas for each one of these. The net 0.1357 here located at 1.1, and the value here of 0.0008 associated with negative 3.15 on the scale here, for a value of 0.1349 or 13.49%. All right, so we can use this standard normal distribution here to really calculate a lot of cool things here. So let's take a look. Let's find the area under the standard normal distribution curve to the left of z is equal to 1.73. Okay, so we're over here now. We've been on this section of the normal distribution curve up until now. Now that we're on this side, are our values going to be greater than 0.5 or are they going to be less than 0.5? Think that to yourself as we're doing this. 1.73 here, that's going to be this portion of the table. 1.73, that's right here, 0.9582. So what does that mean? Okay, that means that 95.82% of the data is somewhere within this section. It's somewhere around the mean. It's going to be at or less this let me back up here for a second. It's going to have a standard. It's going to have a location that is at or smaller than 1.73 standard deviations greater than the mean. In other words, it's either going to be less than the mean or it's going to be greater than the mean, but not more than 1.73 standard deviations. It's going to be somewhere in this blue section here. So 95.82% of the data is going to be somewhere in here. So find the area under the standard normal distribution curve to the left of z is equal to 1.98. That's another one that you can use this same chart to do. Take some time for that. Welcome back. Well, this is a problem very similar to the one we had before, and again, unsurprisingly, it has a probability that's larger than 0.5 because it's on the right-hand side of this curve here. When we take a look at this here, this is more than half of the area under the curve here, so it makes sense that we're going to have a percentage here that's substantially higher than 50%. So what does this say? It says that the probability that we're going to have a data point that's going to be either smaller than the mean, in which case z is negative, or larger than the mean but not greater than 1.98. In other words, it can be larger than the mean but not more than 1.98 standard deviations larger than the mean. What are the probabilities that we'll find a piece of data that's like that? It's going to be 97.61%. All right, so how would we find the area under this portion of the standard normal curve here? Here we're not taking a look at values from this threshold to the left. Notice we're taking a look at values of area from this threshold to the right. So as we take a look at this here, our threshold is still negative 1.24, and we can take a look at this portion here. But what is this describing here? What area is this describing? These areas have always been from this portion to the left, haven't they? And so, caution, this is an area to the right problem in which they're asking what is the area of the standard normal distribution that's right of this threshold here. So what do you think that's going to be? Turns out it's going to be 1 minus this, or 0.8925, or 89.25%. Well, that makes a lot more sense, doesn't it, than 10.75%? That's a large portion of the curve there. All right, so do this one here. It's the same idea. Find the area under the standard normal distribution curve to the right of z equals negative 3.16. Take some time for that. Welcome back. Once again, we have to subtract these values here from 1 in order to get the percentage of the portion of the curve that is to the right of the threshold instead of the portion that is to the left of that threshold. All right, let's take a look at what do we do when we want to find the portion of the normal distribution that's between two separate locations here. Z is equal to negative 1.35 and z is equal to 1.62 here. Well, let's find out what those values of those thresholds are here. Okay, so negative 1.35 is 0.0885. That's what the value is on that funny little scale below 1.35. Let's do the same thing here for 1.62. That's 0.9474, so that would be 0.9474 down here. So as we've talked about before, we take this value, subtract off this value to find the area under this portion of the curve, and we get 0.8589, or 85.89%. So do this one here. Find the area under the standard normal distribution curve between z is equal to negative 1.54 and z is equal to 0.71. Take some time for that. Welcome back here. Well, this is a problem very similar to the previous one in which you had to take a look at two different threshold points, find the values for the area to the left of each one of those threshold points, and in subtracting those off, you find out what the area is under the curve between these 2 points in the standard normal distribution here. And that translates very nicely to a probability. All right, you can also do this somewhat in reverse here. Let's take a look and find the z-value such that the area under the standard normal distribution curve to the left of the z-value is 0.1335. Now this is weird because we've usually been taking z-values and finding areas underneath the curve, and here we're having to do the exact opposite. We're given the area under the curve and we're having to find the z-value. So that's a little different here, but let's read the problem here one more time. Find the z-value such that the area under the standard normal distribution curve to the left of the z-value is 0.1335. Well, if you recall, when we were taking a look at a z-value and finding the area to the left of the z-value on the normal distribution, we were looking for these values here. We would look things up based on this value and this value, and we'd find our answer here. Here we're having to look up these values here and then find our answer here and here. So we have to find, in this case, 0.1335 somewhere in here. 0.1335, these are too small, these are too small, 0.1335. Oh, it's right here. All right, so it's this section here at this point. So what point is that? That's negative 1.11. So it's at that point. So for a z-value of 1.11, you have this portion of the normal distribution at that threshold or to the left. All right, so do this one here. Same idea here. Find the z-value such that the area under the standard normal distribution curve to the left of the z-value is 0.0188. Take some time for that. Welcome back. This is the same kind of problem that we had before, and what we found in this problem was that in order to find just under 1.9% of all of the data in the normal distribution, you want to choose a threshold that's a little more than 2 standard deviations below the mean. Everything at that point to the left is going to be about 1.9% of the data, 1.9% of the area underneath that curve. Okay, let's do this one here. This is kind of a new one. Find the z-value such that the area under the standard normal distribution curve between 0 and the z-value is 0.2123. Okay, so we have to do some gymnastics here a little bit here. This is the same kind of problem as before, in which we're having to find a z-value, but in this case here we're having to find one such that this area right in here is 0.2123. Okay, well, the first temptation might be to find the z-value that has this value somewhere in here of 0.2123. But remember, these values here deal with the total area from this point all the way to the left. And right here, we're just seeing this portion here that ends at 0. So how much more do we get in starting here at 0 and going all the way to the left? And the answer is 0.5. So we're going to look for a location here for a z-value that has a total area to the left of 0.5 plus 0.2123. So that's going to be an extra 0.5 there. So we're actually looking for a location that has an area under the curve here of 0.7123. That's right here. So our value for z is actually going to be 0.56. All right, so in the same way, do this one yourself here. This is the same kind of problem in which you have to find the z-value such that the area under the standard normal distribution curve between 0 and the z-value is this. Take some time for that. Welcome back. We're seeing here a very similar kind of problem with a similar answer here. In order for us to encompass this much of the curve, of the right-hand side of the curve greater than the mean, we have to go out about 1.5 standard deviations to the right of the mean. All right, let's come back to Bradley's problem here, in which we have my middle stepson who is 6 foot 8 inches tall. He's the tallest person in the family. How unusually tall is this? Okay, well let's go through the process of finding out what it is. As it turns out, this is a height of 80 inches, and heights in the United States have an average of 69.3 inches. That's basically 5 foot 9.3 inches, and a standard deviation of 2.94 inches. Okay, so we can use these statistics to figure out how unusual it is that he's got a height of 80 inches. Well, the normal distribution here with a center around 69.3 would be about here, and it's got a standard deviation of just under 3 inches here on both sides. Okay, so Bradley is here at 80. So yeah, that's obviously a very, very high highly, large number of standard deviations above the mean here. Not many people would be at his height or higher. There's not much area under the curve here, not much of a probability of anybody being at his height or taller. But let's go through it a little bit more computationally here. On the standard normal distribution, Bradley's height has a z-value. What is his z-value? Well, we have to take his height, subtract off the mean, and once we have that deviation, that's going to be what? About 10 inches or so. We have to divide that by the standard deviation here, and 10 inches divided by about 3 inches, okay, that's going to be about 3.5 standard deviations above the mean. So he has a z-value of 3.6. His height is about 3.5 standard deviations above the mean. All right, so where is that on the standard normal distribution here? I shouldn't have this part here colored in blue, because we're actually looking here at about this portion way out here, 3.64. That's going to be somewhere between 3 and 4, a little bit more, a little bit to the right of that, so about in here somewhere. Okay, so that's where Bradley is. So let's figure out what is the area under this curve here that starts here and keeps going to the right. So that's the percentage of the area under the curve that starts here and goes to the right. What percentage of Americans are going to have Bradley's height or taller. Okay, so let's take a look at that portion of the normal distribution table here. Bradley's z-value is 3.64 here. Well, he's actually off the scale here. It says that once we get beyond 3.4, for z-values greater than this, just use 0.9999. He is way out here. So 0.9999 means that that the chance that a random person is taller than Bradley is less than 1 minus 0.0999, or less than 100%. So turns out his brothers are correct. He is a mutant from another planet. And so this kind of vindicates that a little bit here. He is very, very unusual in his height. So, and as you can see here with statistics, we were able to not only say that, but actually quantify it with some numbers behind it. Very, very useful as we describe our world. All right, so summarize this, 3 things here. Do you know how to state and to use the z-values for the standard normal distribution? How do you calculate those z-values? Remember, we take the data point, we subtract off the mean, and then once we get that deviation, we divide that by the standard deviation, and we get that z-value. So that's how you calculate that, and those z-values are really, really important, because then you're dealing not with the an ordinary normal distribution, but with the standard normal distribution. Do you know how to state and to use to find probabilities based on areas under the standard normal distribution? In other words, to be given 2 z-values or 1 z-value and find out what's the area under the curve, less than that z-value, greater than that z-value, maybe between 2 different z-values. And then also find z-values, find boundaries on the standard normal distribution based on the desired probability. That's those latter problems that we were doing there, where we had to take a look and find out what the z-value was for some areas under the curve that we were given. That was those last few problems that reversed things for us. So go through your activity sheet, and as a way of summarizing our time together here, make sure that you know how to do those 3 things. That's going to be helpful in our in-class discussion as well as on the homework here. So hopefully that was helpful. Hopefully that wasn't too confusing. And keep in mind that I'll be available online through the Zoom link tomorrow, as well as throughout the new semester here. This is our new reality that we're working with, and I look forward to seeing you in class.